Okay, I'm going to try and provide an overview of what are the basic things from first year chemistry that you're going to need to know in organic chemistry. And I'm going to gloss over all the details that might be relevant if you want a deeper understanding, but you don't need to jump into Orgo. So I'd say number one, the first thing you need to know is that matter is made of atoms. Hopefully you picked that out. From your first year chemistry class. And you want to know that an atom has a nucleus that's positive and small. And that nucleus is going to be surrounded by electrons. There are different ways we can represent the electrons. Sometimes we draw the electrons as if they're in orbit around the nucleus, mainly because that's an easy picture for us to imagine. But it doesn't necessarily describe reality. That's okay. Sometimes we need a simple picture, and this is the picture we'll draw. Sometimes we'll draw more complicated pictures where we'll have the nucleus in the center, and then we'll say, oh, but the electrons are in a cloud around the nucleus. And we could have different shaped electron clouds depending on where those electrons are. So these would represent what we call electron clouds. And you might be like, I don't remember anything about that. No one mentioned that. That's fine. You don't need to know that. Just know that matter is made of atoms. Atoms have a positive nucleus that's in the middle, and then they're surrounded by electrons. And then one other thing you want to know about those electrons is electrons are divided into energy levels. So in this picture with different circles, the inner circle would represent the first energy level. The outer circle would represent the second energy level. If there were more electrons, we might go to a third and a fourth, and so on. The reason we call them energy levels, similar to in physics, how you talked about when an object moves further from the Earth, so moves up, it goes higher in gravitational potential energy. The same is true of electrons, which are attracted to the nucleus. As they move further from the nucleus, they're in higher energy levels because they have higher potential energy. So farther from the nucleus, we would say it's at a higher energy level. And where we're going to focus is on the outermost energy level. The outermost energy level we'll call the valence level. And those electrons in that valence level we'll call the valence electrons. Those are going to be the most important because those are the ones that interact with other atoms when they meet each other. Okay, so you want to know those basic facts about the way we think of matter and atoms. Another thing you want to know is that we have a bunch of elements and we arrange them into this periodic table. We're not going to use most of these elements in this class, so that's good. But one thing that's useful to know is that generally we think of there being kind of a division among the elements. And I'm drawing this as if it's a hard line, but it's really a soft line between what we call metals and what we call nonmetals. All right. So this whole area over here, this would be where we say the metals live. And then this area up here, we would call the nonmetals. I know it's not very creative. And the key thing to know the difference between these: nonmetals have a strong hold on electrons, and metals have a weak hold on electrons. Why is that important? Well, when atoms get together, they usually are going to try to end up with 8 valence electrons around them. We call that the octet rule. And nonmetals and metals employ different strategies for that. When nonmetals are bonding, their first instinct is usually to go and steal electrons from someone else until they get to 8. So if a nonmetal encounters a metal, the nonmetal will steal electrons because the nonmetal is stronger. But if nonmetal atoms meet other nonmetal atoms, they can't steal because they're both strong. So neither one can steal from the other. So they end up sharing. So we end up having these two different kinds of bonding that we'll talk about. When a nonmetal meets a metal, we have stealing, and we call it ionic bonding. When nonmetals meet other nonmetals, we get sharing, and we call it covalent bonding. And the focus of organic chemistry is going to be on this, covalent bonding. So I give you at the beginning of class a periodic table that selects only the elements that you'll see in this class. And here it is. One thing I want you to note about this: almost all of those elements are nonmetals. I did forget to mention on this previous slide that this dividing line kind of extends all the way over here. So hydrogen is also a nonmetal, even though it shows up on the left-hand side. So of the elements you're going to encounter in this class, the vast majority of them are nonmetals. So we're going to be focused on that covalent bonding between atoms. Ionic bonding comes up tangentially, just a little bit here and there, but mostly we're focused on covalent bonding. One other key thing that you want to take from your first year chemistry class is the idea of electronegativity. So I've been talking about metals as being strong and nonmetals as being weak, as if there's a hard dividing line between strong and weak, but really what there is a scale. There's a spectrum from very weak to very strong and everything in between. Electronegativity is that scale that we use. All right, this is a 0 to 4 scale of electron pulling strength. And the key is that when you look at two atoms bonding to each other, by looking at their relative electronegativity values, you can get an idea of who is stronger. Ionic bonding happens when there's a big difference in strength, and covalent bonding happens when there's a smaller difference in strength, so there's more sharing. Okay, so that's a key concept. And I would say the last key concept from your first year chemistry class would be the octet rule. So the octet rule, there's many ways to state it, but I would say the simplest way that I'll state it is atoms tend to end up with 8 electrons in their valence shell. Sorry for the zooming issues. Sorry, I just used the term valence shell. Shell and energy level are used pretty much interchangeably in chemistry. So atoms will tend to end up with 8 electrons in their valence shell. We often represent an atom by writing its symbol and putting dots around it to represent its valence electrons. So if I pick an element from the periodic table, our most common one is going to be carbon. Right here, carbon has 4 valence electrons. So one way to represent carbon would be to draw carbon and put 4 dots around it. I mean, essentially, if we're saying 8 is the goal for any element, I'll use X as a generic element because there's no element named with the symbol X. The goal is to get all 8 of those spots full. So carbon, with its 4 valence electrons, is really looking for a way to end up with 8. Usually it's going to do that by sharing. All right, so a simple way that carbon could end up getting to 8 valence electrons so it can get to a full, what we call a full octet, by sharing with 4 other atoms. So for example, if a carbon were to encounter 4 chlorine atoms, chlorine has 7 valence electrons. That means each chlorine really wants 1 more valence electron. And so this is a perfect match where you could share these two. Oops, I only drew 6 on this one. We could share these 2. We could share these 2. And now both atoms would end up with 8. I could redraw this as carbon in the middle with its 8 valence electrons. Each chlorine has 3 pairs of electrons to itself and is sharing 1 with carbon. And the key here is that the shared pairs count for both atoms. Now, drawings like this tend to get a little hard to see, and so we will often redraw these using lines for the shared electrons instead of dots. Oops. So we'll often redraw this using lines to represent the shared electrons. And we leave the unshared electrons as individual dots. So if I look at any atom here and count the total number of electrons, there should be 4 pairs around it. And chlorine here has 1, 2, 3, 4 pairs. That's 8. Carbon has 1, 2, 3, 4 pairs. That's 8. So everyone is satisfying that octet rule. And we will draw a lot of structures like this over the course of the year. We'll abbreviate more and more, and maybe leave out some of the dots. Eventually we'll leave out the carbon atoms because there'll be so many of them. But I think those are the basic things you need to know to get moving in Orgo.